Welcome, amazing students at Ishik Boys High School.
And a special shout out to Mr. Jager's physics class.
Welcome to For the Love of Physics podcast. We are Mr. Jager's assistant. Today, we're going to do a deep dive into something you literally experience every single day, like constantly. How different stuff around us reacts to heat. You know, think about it. Why does beach sand get, like, incredibly hot?
Yeah, it burns your feet.
Totally. But then the ocean water right there stays pretty cool.
Or even just a hot cup of coffee sitting on the table. It doesn't stay hot forever, does it?
Right, it cools down. So we're going to unpack the actual physics behind these everyday things.
That's right. And we'll explore two really key ideas today. First, specific heat capacity. That tells us how much energy it takes to actually change something's temperature.
Okay.
And second, latent heat. That explains what's going on when stuff changes state, solid to liquid, liquid to gas.
Got it. Secrets to how matter and energy hang out.
Pretty much.
Okay, let's unpack that first one then. Specific heat capacity. Let's use a familiar scene. It's a super hot day, Sarah.
Okay, I'm with you.
And you're about to jump into a swimming pool. The air feels scorching, like an oven.
Oh, yeah.
But the pool water, even though it's been sitting in the same sun all day, often feels way cooler, refreshing even. Why? Why the difference?
Well, that difference is specific heat capacity in action. It's like a unique property for every single substance.
Unique property.
Yeah, it basically tells you how much energy you need to put in to raise the temperature of 1 kilogram of that stuff by just 1 degree Celsius.
1 kilogram, 1 degree Celsius.
And the really interesting bit is if you add the same amount of energy to, say, a kilogram of water and a kilogram of sand, their temperatures will change by different amounts. Some things heat up fast, others are really stubborn.
So it's like some materials are just, resistant to temperature changes. They need a lot of energy pushed into them.
Exactly.
While others heat up super quickly. Oh, like in cooking.
Perfect example.
A metal pan on the stove gets hot almost instantly, right?
Mm-hmm.
But maybe a thick ceramic casserole dish takes ages to really get hot all the way through, even on the same burner.
That's specific heat capacity right there. The metal has a low one, the ceramic the higher one.
And water. You mentioned water earlier.
Water. It has a very high specific heat capacity. One of the highest, actually.
So it's really stubborn.
Extremely. It takes a lot of energy to make water hotter, and it has to release a lot of energy to cool down.
Which is why the pool feels cooler than the air on that hot day.
Precisely. And it's why big bodies of water, like oceans or large lakes, are so important. They absorb tons of heat from the sun without their temperature shooting way up.
Okay.
And they release that heat slowly when things cool down. It helps keep the whole planet's climate much more stable than it would be otherwise, like a giant thermostat.
Wow. Okay, that's actually amazing. The whole planet relying on water being stubborn about heating up.
It really is fundamental.
But how do scientists figure these values out? Like, how do you measure how stubborn something is? Is there a standard way?
Yeah, there is. They use a technique called calorimetry.
Calorimetry, okay.
Sounds fancy, but it's basically an experiment to measure heat transfer very carefully. The main idea relies on energy conservation.
Conservation of energy. Like, energy isn't lost, just moved around.
Exactly. So imagine you have a well-insulated container, like a thermos, with a known amount of cool water in it.
Okay.
Then you take a hot object, maybe a piece of metal, you heat it up, and you drop it into the water.
Right. The metal cools down, the water heats up.
Precisely. And in a perfect setup, the energy the hot object loses is exactly equal to the energy the water gains.
I see. So by measuring the temperature changes of both and knowing the water's specific heat, you can figure out the specific heat of the object.
That's the core principle, yeah. Careful measurement is key.
Okay, so we see how oceans use this to regulate global temperature. What about closer to home, like keeping our houses comfortable? Does specific heat play a role there?
It definitely can. Think about something like Earth-coupled heat pumps. Maybe you've heard of geothermal systems.
Vaguely, yeah. Using the ground.
Right. They tap into the ground's temperature, which is much more stable year-round than the air temperature.
Why is the ground more stable, though?
Well, a couple of things. Earth material, like soil and rock, has a certain specific heat capacity. It's actually generally lower than air's per kilogram.
Lower, so it should heat up faster.
Per kilogram, yes. But the key is density in sheer amount. The ground is way, way denser than air. There's just so much mass of earth beneath your feet compared to the air above.
Okay. So even if each kilo isn't as stubborn as water, there are countless kilos.
Exactly. That huge mass means the ground acts like a massive energy reservoir. It can absorb or release a lot of heat without its temperature changing much at all.
So it stays relatively cool in summer and relatively warm in winter, deep down.
That's the idea, making it a great source for heating in winter and cooling in summer using those heat pumps. It leverages that thermal stability.
It's a neat application. Okay, so far, adding energy means temperature goes up based on specific heat.
Right.
But what about this? What happens if you keep adding energy, keep heating something, but its temperature just stops changing? Like flat lines, that sounds weird.
It does sound counterintuitive, but it happens all the time. This brings us to our second big idea, phase changes.
Phase changes,
Yeah.
like solid, liquid, gas.
Exactly. A phase change is when a substance transforms its state. Solid to liquid that's melting, liquid to gas that's boiling, or evaporation.
Okay.
And here's the kicker. While the substance is actually in the process of changing phase, its temperature stays perfectly constant, even though you're still pumping energy into it or taking energy out.
Wait, really? Constant temperature?
Yep. Think about heating an ice cube you just took out of the freezer. Let's say it starts at, I don't know, minus 25 degrees Celsius.
Okay, freezing cold.
You add heat, its temperature goes up, minus 20, minus
Yep.
10, then it hits 0 degrees Celsius.
The melting point.
Right. And then, even though you keep heating it, the temperature stays locked at 0 degrees C until all the ice is melted into water.
The thermometer just sits at 0 the whole time the ice is melting.
Exactly. Only once it's all liquid water will the temperature start climbing again. 10 degrees C, 20 degrees C, all the way up to 100 degrees C.
The boiling point.
And guess what happens at 100 degrees C?
It stops again while it boils into steam.
You got it. The temperature stays fixed at 100 degrees C as the liquid water turns into gaseous steam. It only increases again if you could somehow keep heating the steam itself.
So where's all that energy going? If it's not making the stuff hotter, it feels like it's disappearing.
It's not disappearing, it's just doing something else. That energy, the energy transferred during a phase change at constant temperature, is called latent heat. Latent kind of means hidden.
Hidden energy. Okay, so what's it doing?
Instead of making the molecules jiggle faster, which is what temperature measures, their average kinetic energy, this latent heat energy, goes into changing the arrangement of the molecule.
The arrangement.
Yeah, like breaking the rigid bonds that hold them together in a solid structure when ice melts, or overcoming the forces that keep them close together in a liquid when water boils. It's changing their potential energy, the energy stored in their positions relative to each other, not their kinetic energy.
Ah, okay. So kinetic energy relates to temperature, potential energy relates to the phase or state.
That's a great way to think about it.
So this latent heat, this hidden energy, is why an ice cube works so well in a drink, right? It's not just that it's cold.
Exactly. It has to absorb a significant amount of latent heat just to melt from solid ice at 0 degrees C to liquid water at 0 degrees C. That energy comes from your warmer drink, cooling it down effectively.
And sweating, when sweat evaporates from your skin.
Same principle. The liquid sweat needs to absorb latent heat from your body to turn into water vapor, cooling you off. Refrigerators use similar phase change cycles too.
Cool. So are there different kinds of this latent heat?
Yep, mainly two you'll focus on. First is the latent heat of fusion. That's the energy needed for melting, solid to liquid. Or, conversely, the energy released when freezing, liquid to solid.
Fusion, like fusing together when freezing or breaking apart when melting. Got it.
And the second is the latent heat of vaporization. That's the energy needed for boiling or evaporating, liquid to gas. Or the energy released during condensation, gas to liquid.
Vaporization for making vapor.
And the heat of vaporization is usually much larger than the heat of fusion for most substances, especially water.
Which explains something, maybe. Why does steam at 100 degrees C cause way worse burns than boiling water at the same 100 degrees C?
That's exactly why. The steam contains not only the heat energy to be at 100 degrees C, but also all that extra hidden, latent heat of vaporization it absorbed when it turned from liquid to gas. When that steam hits your skin and condenses back to liquid water, it releases that massive amount of latent heat, causing a much more severe burn.
Ouch. Okay, that makes a scary kind of sense. It's carrying extra energy.
A lot of extra energy. It's a really powerful illustration of how energy transco works and how these phase changes are, well, not just about temperature.
Definitely. Okay, so let's quickly recap what we covered in this deep dive.
That's good.
We started with specific heat capacity. That's basically how much energy a substance needs to change its temperature. Different materials have different values, right? Like water being very high.
Very resistant to temperature change. Affects everything from cooking pans to climate.
Right. And then we talked about latent heat. That's the sort of hidden energy involved when something changes, phase melts, freezes, boils, condenses.
And crucially, the temperature doesn't change during the phase change itself because the energy is rearranging the molecules, changing potential energy.
Got it. Heat of fusion for melting, freezing. Heat of vaporization for boiling, condensing.
Those are the key takeaways. Really fundamental ideas for understanding how energy and matter interact. You see them everywhere.
Absolutely. Okay, so for your reflection, think about this question. Imagine you're in a really hot room. There's a metal doorknob and a wooden door, and they've both been in that same hot room for hours, so they're at the same temperature.
Okay.
If you had to touch one, which one would feel hotter, the metal or the wood, and why? Think about what we discussed today.
Good question. The answer connects directly back to specific heat and maybe even how quickly heat transfers.
Definitely something to mull over. All right, that about wraps it up for us today.
Keep thinking about physics all around you.
Stay in contact with your physics teacher. Stay creative.